In this video, we are looking at quotient maps. Quotient maps are an auxiliary construction for us here. They are right from topology, meaning that we are only talking about continuous maps, so no differentiability structures here. And we start with two topological spaces, X and Y, and a surjective map, and then we make the following definition. So we call Q a quotient map if U in Y is open, if and only if the preimage of the set in X is open. So what one should think about this definition and about the quotient maps. So in a certain sense, this quotient map completely determines or when sets in the target space Y are open. And so let's state some of the properties of these things. So the first lemma about them. So if Q from X to Y is a quotient map, then part A, Q is continuous. And part B, if, let's say, another map F from Y to a third topological space Z is a map, then F is continuous if and only if the composition of these two things is continuous. Okay, so let's prove this. Well, part A is trivial because, well, recall Q is continuous if preimages of open sets are open. And, well, this is true by definition. Of a quotient map. Okay, and part B, well, so if F is continuous, then we know that also the composition of two continuous maps is continuous. So since Q is continuous by part A, we see that also the composition is continuous. Assume now conversely that the composition of these two guys is continuous. And now we have to see that F is continuous. Okay, so let's see how this goes. So if U inside of Z is open, we have to show that the preimage under F is open in Y. Okay, but since Q is a quotient map, we see that the set F inverse of U, that this is open if and only if the preimage of this set under the quotient map is open. But we can rewrite this, so this is nothing else than the preimage of the set U under the map F composed with Q. And we already knew that this map we have here, this is continuous. So from the continuity of the composed map, it follows that the set really is open. And we can deduce that F inverse of U is open. Hence, F is continuous, thus proving the lemma. Okay, and now what we will need later on is the following statement, which is known as Whiteheads Lemma. And this is a very curious statement. It basically says, so if f from x to y is a quotient map, and Z is a locally compact space, then the Cartesian product of the identity of Z times F, so this is a map from Z times X to Z times Y, and it's the map which takes a pair ZX to Z and F of X. Oh, this was not supposed to happen. Is again a quotient map. Right. And so the important thing is here, this really uses local compactness of the space. We are not going to prove this statement. It's there's just one word of warning I want to put in here. It is really important to remember that in general, the Cartesian product of quotient maps is not a quotient map. Yeah, so we are not going into details here. Check your favorite topology book about this. But we are really going to use at one instance the Whitehead lemma to construct a nice quotient map as the Cartesian product of the identity and of a quotient map. And yeah, so interesting errors happen when one assumes that the Cartesian product of quotient map is always a quotient map. So we have to avoid this.